Chemistry lessons, chemical bonding, covalent. Now we're going to talk about covalent bonding here, and it's going to get a little deep. I need you just to relax, go through it, get a basic understanding, and then we'll get back to just the basics of what you need to know at the end. If you're in AP chemistry, you need to know all of this. Now remember, covalently bonded molecules only happen in non-metals, okay? Non-metals. The only place there are non-metals here on this periodic table are these green and yellow things. And of course hydrogen over here, okay? Many of our gases here can also be covalently bonded at times, but normally they're not involved in this. So the ones you need to really worry about are the hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, selenium, and then of course all of our halogens right here, fluorine, chlorine, bromine, and iodine for sure. Now what we're going to talk about here is what you've been told when you were younger, is that an ionic bond captures the electron and a covalent bond shares it. What we're going to learn about here is something we've already talked about in class, which is electronegativity. And it is just the difference between the two elements' electronegative rating that will determine how strong they pull that electron from the other element. If we have two hydrogen atoms here, then their electronegative rating would be the same. There would be no difference. So as you can see, when they share their electron, they share it equally between the two, okay? And hydrogen and many of the other ones like oxygen, nitrogen, things like that, they will exist in a gas form, which is going to show two of these sharing an electron in its orbit. Now, the ones that do this are the bromines, the iodines, the nitrogen, the chlorine, the hydrogen, the oxygen, and the fluorine. Also known as the mnemonic that we use here is Mr. Brinkelhoff. Okay, so bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine all reside as what is known as a diatomic molecule. Di meaning two, okay? Two atoms. So bromine would always be written, if it's by itself, as Br2. Iodine by itself is going to be I2. Nitrogen, N2. Chlorine, Cl2. Hydrogen gas, oxygen gas, that's why you call it O2, and fluorine gas. These will always reside in just being a diatomic molecule, okay? So just remember Mr. Brinkelhoff, and anytime you see any of these by themselves, they're going to exist in a diatomic molecule. Now when we compare covalent bonds to ionic bonds, as I said a minute ago, we're looking for the difference in their electronegative rating. The bigger the difference in the electronegative rating, then the more it's going to pull that electron towards this other proton or this other nucleus here, the protons inside that nucleus. The less anyways the electronegative rating difference between the two, which we'll show you the comparison here in a minute, then they will do a more equal amount of sharing. If I was to take a look at just like hydrogen and carbon, the electronegative rating between those two is very, very similar. Okay, so carbon has a little bit more, so when they would be bonded here, what we would be showing would be a cloud that would be a little bit bigger over the carbon and a little bit less, and it would look more like this, okay? It's going to be more of a sharing, and that's the same way in ionic bonding up here. This cloud, if we were looking at like chlorine bonded to sodium, then this sodium here, this electronegative rating of chlorine is very high. Sodium is very, very low. So this cloud, these electrons from this sodium valence electron is going to spend more time around that chlorine. So you're going to end up with this electronegative cloud that's going to be like this. It's not that chlorine takes the electron away from the sodium, it's just going to spend more time over here because it's pulling it stronger than does the sodium. Here are some examples of just some basic covalent bonding. And all we're looking at is the difference in the electronegative rating. Now these structures here is something we're going to work on also in class, but they're called Lewis dot structures, okay? And this is how we work with just the valence electrons, okay? We're only working with the valence electrons on the outside shell, because they're the only ones that are that are involved in this bonding that's going on. And the difference in the electronegative rating is going to determine whether this is a covalent bond or an ionic bond. Remember, electrons are not captured or travel in orbits around a nucleus like we draw. We draw that so it makes it look very easy. Actually, electrons, I'm just going to put a bunch of extra dots, I'll put them in red in here, but electrons can just end up in different areas, okay, around here. It just all depends on where they spend their time, okay? If they spend more of their time over here, then you're going to have a bigger electron cloud over there. They do not travel in perfect circles around here. Okay? It depends on the energy that electron has, how far it can be away from the nucleus. The less energy it has, it's going to spend most of its time closer to the nucleus. Now, here's the electronegative rating that I was talking about. Okay? If we are greater than 2.1, okay, then it's an ionic bond. We label that as an ionic bond, okay? So that means that electron is going to spend more time around the negative ion than it is around the positive ion. The closer the electronegative difference is between the two, then we start to determine, covalency. As you can see, these here are both covalent. One just becomes polar and nonpolar, and we'll talk about that at a little bit different time. So here's a quick look, okay? Just a brief review. A nonpolar covalent means it's going to spend equal time around both of them. Polar means it's going to spend more time around the one and less time around the other, so there's more of a negative side and more of a positive side. Think of it as like a magnet. Here it would be like positive ends or two negative ends of a magnet, okay? There's no difference between one or the other. And an ionic bond is going to have where that electron is going to spend almost all of its time around the negative one, but it still will spend some time around the positive, the metal here, and it just gets a little bit bigger of a negative cloud around the chlorine here, okay? And the reason that we're looking at this is the difference in electronegativity. So that's what we're talking about when we talk about a covalent bond. It shares. All of our polyatomic ions are covalent. So when we look at this, we're going to say, okay, we've got those covalent bonds that like we've got nitrogen and hydrogen, and there's 4 of them, okay? That's a covalent bonded molecule. Okay, our oxygen and hydrogen, which is hydroxide, is covalently bonded molecule, okay? So any of these that we're writing up here that we have to be able to, memorize, these are all covalently bonded molecules. And if you remember, these are also polyatomic ions, and they will not, the covalent bonding is so strong, they will not break apart, whereas the ionic bond will break apart, okay? So in covalent bonded molecules, all we have to remember is that the electron is going to be shared more evenly around all of the different elements that are involved in that compound, whereas in an ionic bond, it's going to be a more even or uneven sharing. It's going to spend more time around the anion and less time around the cation. Now, while this could be, a little bit of difficulty in understanding covalency, the biggest thing will be when you look at the video on covalent naming. We use a Greek naming system, but right now you just need to understand what do we mean by a covalent bond. Ionic bond is between a metal and a nonmetal, and covalent bonds are between 2 nonmetals, and there's only a few of them on the entire periodic table that you got to worry about. Remember, chem is try, never ever give up, and stay gritty out there.